Those are all good. Those are all good. I will begin with a word of prayer. So, Dearly Father, we thank you for this day. I thank you for the students. Just ask you to bless our time together, Lord. In your name I pray. Amen. Well, just so you know, if classes are canceled mid-lecture, I am still going to go to the complete time of lecture. I understand if you need to leave out of principle, but I will continue talking. I'm assuming. If it doesn't, if it doesn't happen, it would be kind of like surprising, right? Like. Oh, they've already said you can miss if you feel like it. But they've already basically given you carte blanche to miss tests today, is what you're telling me. Okay. All right, let's see here. Let me begin with an example for you guys. Let's try to solve y prime prime plus 4y prime plus 5y equals to, let's say, t, such that y of 0 equals to y naught and y prime of 0 equals to y1, where these are given but arbitrary. All right. In other words, we want to solve the initial value problem. All right. So the way to do this is to take the Laplace transform of both sides. So we take the Laplace transform, right? And that gives us s squared big Y minus s times y naught minus y1 plus 4 times parentheses s big Y minus y naught plus 5 times big Y equals to, well, what's the Laplace transform of t? I believe it's 1 over s squared. Right? Yep. All right. Table 7.1. Oh, by the way, lest I forget, you can put your name on there. Call it attendance. All right. So then do the algebra. We've got ourselves an s squared plus 4s plus 5 times big Y equals to, what we got? We got s y naught plus, or rather minus, oh, I'm sorry, rather plus because I'm moving the other side. So plus 4 y naught. All right, great. Plus 1 over s squared. So what do we got? We got y plus, oops, excuse me, big Y equals to 5 y naught plus, good grief, that's not a 5, that's a what? Yeah, I'm a victim of my own handwriting. So this was an S, right? There's also a 5 in this problem. It's unfortunate, isn't it? 5. All right. So S, grief, S y naught, oh, I forgot to do what here? Plus y1, right? Let me just reiterate here. I've got 3 terms coming from initial conditions. I've got this one, which is giving me that. I've got this one, which is giving me that. And I finally got this one, which leads to that. All right? Are we good? Sorry about my previous mistake. And then so in total then we have s times y naught plus, and I'll put some parentheses on this, 4y naught plus y1, all divided by s squared plus 4s plus 5, and then plus 1 over s squared times s squared plus 4s plus 5. Now I need to take the inverse Laplace transform of both sides, right? This question? Okay. So I would point out that this is actually equal to s plus 2 times y naught plus something divided by s plus 2 quantity squared plus 1. So the reason that I made an s plus 2 appear at the start there is because I need to find like s plus 2 over that denominator in order to use the inverse transform. Right? If there's an s plus 2 quantity squared plus 1 appearing, I need an s plus 2 in the numerator as well to see inverse cosines. But to be fair, I had 4 y naughts before, right? So what's left over here is just 2 y naught plus y1. Right? All right. And then this piece over here, whatever that works out to, right? So I'm going to put some big old parentheses here. We're gonna have to do some work on that. Question? No? They're a bad influence on you, Ian, aren't you?
I was just trying to determine if it was an S or a 5. I'm sorry. Yeah,
All right, fine. I mean, fair enough. If that's a problem for all of you guys, we don't have to do Laplace transforms in S. You could use some other letter if you don't like S. I mean, kidding aside, you could use alpha, lambda, even x, right? Because we're using time domain, you could make x the Laplace transform of t. Anyway, but I will continue using S as it is our custom. Now, this piece, I can already tell you what the inverse transform of this is, right? So like y is equal to the inverse transform of big Y, and as a function of time, of course. So let me tell you, I'm going to start the process here. I can already do it on this piece. So what I'm looking at here is a y naught e to the minus 2t cosine t plus 2y naught plus y1 e to the minus 2t sine t. I'm using the table and the fact that remember, we worked this out, the Laplace transform of e to the alpha t cosine beta t is equal to s minus alpha over s minus alpha squared plus beta squared, and also the Laplace transform of e to the alpha t sine beta t is equal to beta over s minus alpha squared plus beta squared. So I keep these in mind as I'm doing the inverse transform, all right? I don't leave these up here for our future reference today. So at the moment, all I've done is taken the inverse transform of this piece right here, okay? Are you guys with me on that? Here beta is equal to 1, so it's kind of a little bit simpler than it is otherwise. But that's it. I completed the square in the denominator. That's always a good move. Okay, so let's take care of the other looming question, which is what about that 1 over s squared times s squared plus 4s plus 5? Well, there we need to use partial fractions, right? So this other piece, 1 over s squared times, well, s plus 2 quantity squared plus 1, really, right? So let me call this thing f of s, let's say. So f of s. And then how does that work out? Well, this is going to give me an a over s plus a b over s squared plus c times s plus 2 plus d over s plus 2 quantity squared plus 1. Now, I write the last term in terms of s plus 2 rather than s upstairs because I'm anticipating the inverse transform that I'm going to do. So I might as well have an s plus 2 multiplying the c because it makes the inverse transform that I will soon do much easier. All right? But here's the partial fractions decomposition for this quartic in the denominator. And then we do the usual song and dance, multiply both sides by the denominator. What's that give us? We get as plus b times, s squared plus 4s, oh fine, s plus 2 quantity squared plus 1. Then we got plus s squared times, see, I'm assuming that Ian's only saying that because he's sitting next to them. They're a very bad influence on you, Ian. I see that now. I see that now. Ooh, oh man. Oh, I really want to read that email. All right, I must not. Okay, are you guys with me? Let's multiply both sides by the denominator. Am I going to have to move you two? I'm going to have to separate you two, aren't I? That's what this come to. What's that? Those actuarial majors, right? They've been acting up again. I guess it makes sense. To make up for last week. All right, so I suggest we put in some values that we like. For example, I like s equal to 0. That's very lazy. 1 is equal to b times what? 5? Yep. So therefore, b is 1/5. Well, that's good to know. 1 constant down, 3 to go. What else should we put in? I think s equals to minus 2 is a good choice, right? What happens with that? We get minus 2a plus 1/5 times 0 plus 1 plus my s squared was 4 times c times 0 plus d. I mean, it's not awesome, but it's at least a pretty nice equation, right? So like 1 is minus 2a plus 1/5 plus apparently 4d, yeah? So let's put that in our memory bank and move on and find another equation. What can we do next? So this one, it probably pays off to equate coefficients of different powers of s, right? We've been able to plug in values to get equations, but the other thing you can do is to multiply it out and look at this in terms of, I mean, if you can just try to visualize it. This is something times the number 1, right? Plus something else times s, plus something else times s squared, plus something else times s cubed, right? And for that to be equal to 1, it follows that whatever you put in these parentheses have to be separately equal to 1, right? Equal to 0, equal to 0, and equal to 0, equating the coefficients of the polynomials in S on both sides. So let's look at it from that perspective and collect some things. What do we got here? For the S term, what does that give us? What can you get from multiplying just pure S's? I got an A. 1 times AS gives me A. First of all, I got 0 on the left-hand side, so 0 is equal to A. And then is there any other S's in here? Well, this multiplies back out to what? This is actually S squared plus 4S plus 5, right? This whole thing. So, yeah, I get the 5 times A, which gives me the, wait a minute. Oh, see, I made a mistake. What is it? Is it A? No, it's 5A. Let me get away with that. 5A. Thank you for correcting me on that. So 5 times A, but also 4 times B. That's from the first term. Are there any S, just plain S's in the next one? There are not, right? Because that has at least order S squared. Oh, hey, this is fantastic because this tells me that A is equal to minus 4/5 B, right? But we already know B was 1/5, so this is minus 4 over 25. Well, that's very nice because when you put that together with the star equation, it tells us what D is, right? So we can find D. What's D equal to? What's 1 minus 1/5? 4/5, right? 4/5 plus 2A divided by 4 should be equal to D. And, oh, so that's 1/4 of 4/5 minus 8 over 25, apparently. Multiply the first by 5 over 5. I got 20. 20 minus 8 is 12. So I get 12 over 4 times 25, also known as 3/25, right? So 3/25 would seem to be our D, if I haven't made a mistake. If you point out a mistake at the beginning of this calculation at this point, I kill you. What's that? It might be. Well, this is 20 times 5 over 5, right? So that gives me 20 minus 8, which is 12. So I think it's okay. Now, how do we get another equation? Well, continuing with my equating coefficient scheme, let's look at the coefficient of S squared. What do we got there? Or should I do S squared, or should I do, well, I can do S squared anyway. So S squared here, you got what? You've got 4A. 0, obviously on the other side. 0 equals to 4A. Are there any other S squareds I got? Yeah, A times 4. Plus B, right? From the first term. And then over here I got what? Just 2C plus D, right? Well, that's kind of a horrible equation. It's got all the letters in it. But that's not bad because we know 3 of them, so we can figure out the 4th, right? So let's do it. What's the one we don't know? I got my A, B, C, right? I got to get C. So C is equal to minus 1/2 of 4A plus B plus D. So that's minus 1/2 of minus 16 over 25 plus 1/5 plus 3/25, which is really minus 1/2 of minus 16 plus 5 plus 3 over 25. Which is a minus 8 over 25. I think that's 4/25. All right. So it was kind of a pain, but we figured it out. The partial fractions decomposition of this, my a is minus 4/25. So I've got minus 4 over 25 divided by s. What was my b? Well, 1/5, right? So plus 1 over 5 divided by s squared. And then plus, so here I've got s plus 2 quantity squared plus 1. My c was 4/25. So 4/25 times s plus 2. And my d plus 3/25. Yeah? So now we have done the algebra, which now allows us to take the inverse transform of the thing I just wrote down with ease, right? So the inverse Laplace transform of minus 4/25 over s is just minus 4/25. So I get minus 4 over 25 plus t over 5. And then plus 4/25 e to the minus 2t cosine t plus 3/25 e to the minus 2t sine t. And there you go. Answer. So I did two kind of hard things in this example. The one was that I dealt with having initial conditions which were given but not specifically numbers that you could kind of tangibly hold on to, right? I used a y naught and a y1. But we can solve problems like that. We just have to think about the appropriate patterns to match. It's not a big deal, really. And then the other piece, of course, that's a pain is that I put a t on the other side, right? So that makes the partial fractions a little bit harder. Any questions about what we did? It seems to me we could solve an associated problem. Let me do that. Suppose you wanted to solve y prime prime plus 4y prime plus 5y equal to, I don't know, how about the unit step function of t minus 3 minus the unit step function of t minus 2. All right, and we'll just keep things simple this time. We'll let y of 0 equal y prime of 0 equal to 0 because I don't want to keep belaboring that part. Right, so that makes the red part of the solution kind of go away. I want something a little bit worse than this. I don't want to make it too bad. Yeah, I think I can multiply those by t, and we can still do it without a bunch more algebra. Let me take that for a spin. Let's see if I'm right. All right, so what's the Laplace transform? We've got ourselves s squared big Y plus 4s big Y plus 5 times big Y, taking the Laplace transform. What's the Laplace transform of t times u to the t minus 3? How's that go? Looks like I'm going to be wrong. I'm going to have to change those up a little bit to make this life easy. Like, this is not going to work for us. I'm going to have to change that up a little bit. I'm trying to make this problem so that we don't have to reinvent the wheel and do another 10 minutes of algebra. So I need to tinker a little bit. So I'm still going to make initial conditions be 0, but I think what I want to do is to make this t minus 2, or t minus 3 times u of t minus 3, minus parentheses t minus 2 times u of t minus 2. I think if I do that, we'll have a nice example. All right. So if we go back to the theorems we derived last time, one of the things we derived, of course, was that the Laplace transform of g of t times u of t minus a, right, is equal to e to the minus as times the Laplace transform of g of t plus a. So in particular, this says that the Laplace transform of t minus 2 times u of t minus 2, right, is e to the minus 2s times the Laplace transform of, well, t plus 2 minus 2, right, which is what? What's the Laplace transform of t? It's 1 over s squared, right? This is what I wanted to engineer to happen, all right? So the point here is the Laplace transform of these terms works out to 1 over s squared e to the minus 3s minus 1 over s squared e to the minus 2s, all right? So the first step in any of these problems is to take the Laplace transform of the differential equation and, deal with that, all right? So we did that. Now we solve for big Y. And this gives us big Y equals to, well, 1 over s squared times s squared plus 4s plus 5 e to the minus 3s, right? Plus, well, minus 1 over s squared times s squared plus 4s plus 5 e to the minus 2s. So you can recognize what we're looking at is what? Let's put it in terms of my previous name calling. We've got what? We've got y equals to y of s, if you like. Y of s is equal to f of s e to the minus 3s minus f of s e to the minus 2s. And remember, we just did a bunch of calculation to show that this, this thing right here, right? This is f of s, right? Whichever way you want to look at it. 1 over s squared times s squared plus 4s plus 5? Sure, useless. Or the partial fractions decomposition, which we worked out. All right? So when I'm taking the inverse transform of something like I just wrote down in black, we need to understand how to nicely decompose the big F of s. Now I'm going to erase the algebra here. We don't need it anymore. So how do I take the inverse transform of big Y to get my answer? So little y of t is equal to the inverse Laplace transform of f of s times e to the minus 3s minus the inverse Laplace transform of f of s times e to the minus 2s. Now I use a theorem, right? we derived last time. The theorem says that that's equal to f of t minus 3, u of t minus 3, minus little f of t minus 2 times u of t minus 2, right? Where the Laplace transform of little f is equal to big F. So what's the little f here? What's the inverse Laplace transform of big F? I already have it written in purple over here, right? This purple, the last bit, well, really the non-homogeneous part of the solution to the last problem is the little f. This is f of t, because this is the inverse Laplace transform of big F. All right, so now all I got to do is basically piggyback the calculation of the last example to this one, and I have my answer. So here it is. So it's going to be kind of long, but here it is, minus 4/25 plus t minus 3, t minus 3 divided by 5, plus, and I'm going to do something here, guys. I'm going to factor these out, okay? I'm going to factor that out. So I've got 1/25 e to the minus 2 times t minus 3, right? Times parentheses 4 cosine of t minus 3 plus 3 sine of t minus 3. And then all of this whole deal, all of that, all of it, times u of t minus 3. What I just wrote down is merely the details of what's meant by f of t minus 3 times u of t minus 3. And then we do the same thing, replacing t minus 3 with t minus 2. But subtract it, right? So minus 4/25 plus t minus 2 over 5 plus 1/25 e to the minus 2 times t minus 2, 4 cosine of t minus 2 plus 3 sine of t minus 2, and big old parentheses here, u of t minus 2. There you go. Now, if you find yourself faced with a problem like this, it's important to identify algebraic tasks that don't need to be repeated, right? Like finding the partial fractions decomposition of f of s is an intrinsic difficulty of this problem that if you're not paying attention, you might find yourself doing it twice. But you only need to do it once, but that one time has to be differently applied for the different terms, right? Like the same algebra guides this piece and that piece, but, you know. All right. Any questions about what we're doing? Let me try to do a little bit easier example, yeah? No? Okay. So I think I can, let me kind of dial it back a bit here and do a slightly easier example. Let's look at y prime prime plus 6y prime, rather minus 6y prime, I should say, plus 13y equals to I don't know. What do you guys want from me? Oh, I was going to make it easy, right? So Kronecker delta, direct delta of t minus 3. There we go. And we'll suppose that y of 0 equals to 1 and y prime of 0 equals to 7. Solve this problem. Okay? Let's do it. So here we go. We've got s squared big Y minus s minus 7 minus 6 times s big Y minus 1 plus 13 times big Y. What's the Laplace transform of the direct delta function? Is just the exponential in the s domain, e to the minus 3s. We derived that last time. Now I do algebra. So algebra, I've got my s squared minus 6s plus 13 times big Y equals to, oh, I got here. I've got an s. I've got a minus 7 plus a 6, which gives me a net of minus 1, so plus 1. And, oh yeah, plus e to the minus 3s, right? Now we divide by the characteristic polynomial in S. This gives us y equals to s plus 1 over s squared minus 6s plus 13. Okay, interesting. S squared minus 6s plus 13 times e to the minus 3s. All right, so looks like we're not going to have to do partial fractions this time. Actually, it's not clear yet. Our next move is to complete the square in the denominator. After we complete the square, we're going to see that we have a sum of squares, which means it's an irreducible, which means we're going to get sines and cosines, right? We just have to kind of deal with it. Of course, we also have to deal with the theorem I erased from this one, right? All right, so let's see here. We've got y is equal to, well, let me just off on the side here. Downstairs, we've got s minus 3 squared plus what? Plus 4, right? And so I need to create an s minus 3 upstairs. So if I do that, I've got s minus 3, great. But to be fair, I had a 1 before, right? So what do I have to put? Plus what? Plus 4, right? Leave myself a little room there. See, that 4 is actually 2 squared, isn't it? So when you look here, you need a 2 for the sine transform. So what I think about doing is to take the 4 and to essentially say, okay, well, that's really times 2 over 2. Well, I don't know. So here it's too easy. Dang it. I wanted that to be messier. Is it too late, guys? Can I change that 7? It's too late, isn't it? Fine. That 4 I'm going to write as 2 times 2. All right, and then plus 1 over s minus 2 squared plus s minus 3 squared, rather, plus 2 squared, e to the minus 3s. Now, aha! Now I've found a legitimate use. So here, I'm going to rewrite that 1 as a 2 times 1/2. All right, there, I'm happy. I've found a legitimate place to exhibit the trick right there. See, because you need a 2 up there for the sine transform in this case. That wasn't an issue in the previous problem because we had beta equal to 1. It's like it wasn't an issue, this arithmetic. All right, so let's give this a name. Let's call this whole deal f of s again. All right. And so what's y? The inverse Laplace transform of big Y, right? And from the first term, what do we got? We've got e to the minus 3t cosine of 2t plus 2 e to the minus 3t times the sine of 2t. And just to emphasize, this 2 you could think of as being that 2. All right? Now, on the other hand, let me just a little side calculation here. What's the inverse Laplace transform of big F? Big F does not include the exponential, guys. I've got 1/2 times e to the minus 3t sine of 2t. I heard that. That's my little f of t in our usual notation. But what's the theorem? Inverse Laplace transform of f of s times e to the minus as is equal to what? It's equal to little f of t minus a times u of t minus a. You need to do these enough that you don't get confused about what you're doing. There is a mental block to get past here for most students, right? Like, you make sure you have settled what I'm currently talking about before you hit the test. It will get you otherwise. I know from experience, this is the part of it that students get hung up on, using what I just wrote down. Because you don't always use it, right? The first part, what I just wrote down here, we didn't use it. That's just the inverse transform of the first piece, right? But then over here, we're multiplying by e to the minus 3s. So here I have to use this theorem, right? And so the way that happens in this one is plus 1/2 e to the minus 3, not t, but t minus a, which in here is t minus what? Minus 3. Then the sine of 2 times, well, again, t minus 3. And then all times the unit step function of t minus 3. Notice that the 3, which appears in the unit step function, and the 3, which appeared in solving the characteristic equation, these are coincidental, right? Those are different kinds of 3's in some sense. But there you go, answer. Any questions? One more example, and then I'll show you guys some stuff on the projector. So another problem that often comes up with Laplace transforms, in fact, I don't have a good one handy, but you can ask mixing tank problems where you have a couple different mixing tanks and one feeding into the other, and those will give you a differential equation. Maybe I can come up with one. Let's try. So suppose you had let's say X kilograms salt in this tank, and we have another tank over here where you have Y kilograms of salt. And then suppose that you have a couple pipes, right? One pipe going from here to here, like that, right? And suppose that these 1,000 liters each. These are both 1,000-liter tanks, right? And you have flow pipes going from one to the other and the other to the one, right? And let's suppose that you have, 100 liters per minute that way, and you've got 100 liters per minute the other way. Then you could set up differential equations which study how initial concentrations of salt in the two tanks transfer, assuming they're both well mixed. Right? So let's, for the sake of discussion, suppose that x of 0 is equal to, 100 kilograms of salt, whereas y of 0 is equal to, well, let's suppose it's initially got no salt at all. Then you can study what happens as time goes to infinity and these mix. I mean, you know what's going to happen, right? It's a closed system, so the 100 kilograms is just going to get mixed uniformly throughout both. Eventually, we'll have 50 kilograms in each, right? How does that play out, though? What's the dynamics of that? We can use differential equations to solve it. And so, for example, we would say dx dt equals to what? So the rate out, or rate in, rather, minus the rate out. So how do we get, how many, and let's use t in minutes, of course. So what's the rate in for x? Where's the input coming from? It's coming from y, right? So the rate in would equal to, what we got? 100 liters per minute times what? Times y over 1,000 liters, right? So y over 1,000 is the concentration, the amount of kilograms of salt per liter. I multiply that by liters per minute, that gives me kilograms per minute transferred in, just by dimensional analysis, if nothing else. So 100 times y over 1,000 should give me the rate in. And what's the rate out? Minus 100 times L over M, x over 1,000. Right? So dismissing units here, we've got dx dt is equal to apparently 0.1 y minus 0.1 x. And in a similar fashion, we can find the equation for dy dt, right? So in the same fashion, dy dt should be the rate in minus the rate out, which when we think about y, we've got 100 liters per minute, right? And where's y coming from? So x over 1,000 minus 100 liters per minute times y over 1,000. In short, we face dy dt equals to, 0.1 x minus 0.1 y. Well, this is a system of differential equations, right? So what are we facing here? We're facing dx dt equals to minus 0.1 x plus 0.1 y. And we've got dy dt equals to 0.1 x minus 0.1 y. And this is with x of 0 equals to what? 100. And y of 0 equals to 0. So after the setup, what do we face? We face a pair of, a system of differential equations with initial conditions given. Laplace transforms are actually a great way to solve these if you're not a fan of eigenvectors. So how many of you guys are not fans of eigenvectors? Don't answer that.
Go eigenvectors.
Go eigenvectors. Seems entirely organic, the comment. It seems from the heart. Okay, all right. But the point is, actually, you could solve this with Laplace transforms without any knowledge of eigenvectors at all, just by brute force algebra. Because once you take the Laplace transform, we'll have two equations and two unknowns in the frequency domain. Let's do it. So take the Laplace transform of both sides. We get s times big X minus 100 equals to minus 0.1 times big X plus 0.1 times big Y. We just need a big X and a big Y because we're transforming both X and Y here. And likewise, Laplace transform of the second equation gives me s times big Y equals to 0.1 big X plus, well, minus 0.1 big Y. And now I got two equations, and I got to solve them, right? I hate these 0.1s, so if you don't mind, I'm going to multiply both of these equations by 10. All right, so like, what do I got? Multiplying by 10, I've got 10s x minus 1,000 equals to minus x plus y, yeah? And 10s y equals to x minus y. How would you solve these equations now that I've gotten rid of those horrible decimals? I mean, substitution probably is a good way. Take the second equation. What do we got? X equals to what? How about 10sy minus 10sy plus y, right? So solve for big X. I did it. Take that and then plug it back up into here, right? So let me clean this up a bit. We've got 10s plus 1 times big X equals to 1,000 plus y. Now I'll make my substitution, which is 10s plus 1 quantity squared. See, because this is really 10s plus 1 times big Y, right? So you see you've got 10s plus 1 quantity squared times big Y equals to 1,000 plus y, which then by algebra gives me big Y is equal to 1,000 divided by 10s plus 1 quantity squared minus 1. And let's do some more algebra here. We get 1,000 divided by 100 s squared plus 20s. Oh, plus 1 minus 1, so just that. Oh, look at this. What do we need to do? Can you take the inverse Laplace transform of that? I can't. So I need to partial fractions, right? On the last piece, what's the partial fractions decomposition of that? I can factor an s out, right? That's like 20s times 1 plus 5s, yeah? So I would see partial fractions decomposition that would be convenient for me would be a over s plus b over 1 plus 5s. All right? So what do we got? We got 1,000 is a times 1 plus 5s plus b times I guess well, Gotta be careful here. I just multiplied by s times 1 plus 5s. So if I do that, I don't have 1,000 on the other side. What do I have? Think about it, guys. I just multiply both sides by just this, right? So this is left over. What's 1,000 over 20? I heard a 50. I heard a 5. I'm going to go with a 50. Maybe the 5. The 5 was a 50 in progress, I think. So, all right. So there you go. 50 is equal to that. And so what's A and B? Well, may I suggest we put s equals to 0, which will give us 50 equals to A. Aha. Well, apparently A is 50. And if we put s equals to, let's say, minus 1/5, then we've got 50 is equal to A times 0 minus B over 5. Apparently, B is equal to minus 250. So in short, my y was actually equal to 50 over s minus 250 over 1 plus 5s. At this point, I have to face the music, which is to rewrite it a little bit more. This is 50 over s minus, well, divide the top and the bottom by 5. So dividing the top by 5 gives me 50. Dividing the bottom by 5 gives me s plus 1/5. And the reason I would do that is because now I can take the inverse Laplace transform, right? It's always about inverse Laplace transforming. So inverse Laplace transform of that guy gives me y of t, which would be, well, 50, right? Minus 50 e to the minus t over 5. So there's y as a function of time. How to find x? There's a same process would be like completely logical, reasonable way to do it, but wasteful. See, because I can figure out what x is. Oh, maybe that is still the fastest way. Sometimes you look back at the original differential equations and you can like just differentiate y to find x or something. But you're right, I can't. I mean, I don't know, I'm debating. See, if I differentiate y and put it here, that's probably the fastest way to find x, just to go back to this equation. But maybe, I don't know, I'm debating what's the best way to find s. I guess at the level of Laplace transforms, if I go back to this equation, this gives me x, right? Does that help? Does that make it easy? I still think it's a lot of work. I'm kind of on the fence here how to find, what's the best way to find x. I guess I'll just do, I'll Laplace. I'll do the Laplace. So big X is equal to, but I debate whether the time domain way or the frequency domain way is the smartest way here. So 10s plus 1 times big Y, which was, of course, 50 over s. And here's another question I have. I'm using the algebra that we just worked out. Is that smart or is that dumb? Right? Is this going to be easier? Or what if I go back to my previous version of x of y, which was what? 1,000 divided by 20 s times 1 plus 5s. Which one is more advantageous to me as I think about solving for x? Which should I go with here? Which would be easier?